So, all participants, welcome to the third session of today. And the speaker is Dr. B. Suryanarayan sir. He will deliver the talk on the subject of graph theory again. Okay, over to sir.
Visible?
Yes, sir, visible.
In the morning section, we saw different way of representing the graphs and extension of the earlier sets and definitions of simple graphs. Nowadays, graphs are most useful in the form of hypergraphs only. Today, I will take only the application of simple graphs, and its extension can be made easily by the way how you studied morning section. The representation, different representation can be used to write a different matchings. Let us now begin with the topic of matchings. Here we will study first matchings and different forms of matchings and its applications in social systems, also in some other systems. But before that, let us see that every graph can be written as a bipartite graph. Okay. For example, suppose you have a graph like this: A, B, C, D. This graph. This graph is not bipartite. Somebody maybe those who are knowing bipartite can write, can understand. Now, this graph can be written as a bipartite graph. That means some number of vertices should be here in V1, and some number of vertices should be in V2. If there is any edge between, there should be between a vertex of V1 to vertex of V2. No two vertices in the same set are adjacent. For example, this graph is not bipartite. For example, you take now A here, A here. C cannot be in this because C is adjacent to A and B cannot be. So C should be here. Then the edge AC will appear here. After writing C, where should be B? B cannot be in the set containing C. So B cannot be here. B cannot be here. B cannot be in the set containing A. B cannot be here also. So there is no choice for set for B. Therefore, this graph is not bipartite. Okay. However, this graph can be represented as a bipartite graph or some other graph. For example, for that, what you do now, you take the vertices A, B, C, D, replicate it. Again, write A, B, C, D. Okay. Now, AC is an edge. Therefore, from A to C, write an edge. So this edge over. Next, AB is an edge. So from A to B, write an edge now. A to B, write an edge. Similarly, A to C you written. From A to C also you write here. First one, first edge. Second one, A to B written. So I write now B to A also. Next, B to C. So B and C, B to C here and B to C here. This you have to add. This is C to D, C to D, and this C to D. So this is a bipartite graph. So this is one partition V1. This is another partition V2. The given graph always can be represented as a bipartite graph of order twice the order of the given graph. So therefore, I'm thinking about only bipartite graph today. Most of my talk runs around the bipartite graphs. Let us now See the definitions and application. What is matching? Let us see what is matching. A matching in a simple graph is the set of edges with no shared endpoints. Okay. Let us take one example. That's also called the independent set of edges. Matching is a set. It contains some of the edges of the graph G such that if you take any two edges, they don't have a common point vertex, sharing point or end vertex. That means they are not edge set. Independent set of edges. For example, let us take this graph. Okay, let us choose some of the edges here. If I choose this, if I choose this edge, see red, yellow, this edge I choose. If I choose this edge, I cannot choose this and this because they are adjacent. So they have the common end vertex, common sharing vertex. So if I choose just first one, the second, and the third, fourth, fifth side. So if I take only these edges, my set S contains only first edge, second, and third, fourth, five, six edges. These 6 edges, then that is an independent set. Okay. Similarly, I have one more independent set for this. This is also possible. So no two red edges are adjacent. That means no two edges share the common vertex. So now this one set, another possibility, both contain 6 edges. Okay. Now, can you find a set which contains more than 6 edges? It is not possible. You check now. Check afterwards. If you choose any 7 edges, at least one pair share the common vertex. So I hope you understood now matching. Matching is not unique. You can match this vertex, you can match with this vertex. Okay. Then don't match this vertex to another vertex. That they should be adjacent. Okay. There's a meaning for there's an important application of this matching definition. Later we'll see. For example, let us now take this one. This is also another matching. This also contains 6 vertices. Okay. 6 edges. Okay. The vertices incident to each edges of a matching M are called saturated by M. For example, you take this edge. Suppose you take the matching of containing only these green edges. This green edge is incident with this vertex and this vertex. Therefore, these 2 vertices are saturated by this edge. And these 2 vertices are saturated by this edge. Okay. If I take M, set M consisting of only green edges, okay, all the vertices are saturated by one edge except one vertex. So for example, you take this set vertex. This vertex is not saturated by any edge because this is not incident with any edge in M. So this vertex is incident with one green edge. This is incident with this green edge. And this vertex also incident with one edge. So this vertex, except this vertex, all the vertex are saturated by these green edges. Green edges are nothing but my M, set M. Now, so this here, second one, we have this vertex. You say this vertex, the third. This vertex is not saturated by yellow edges, containing M set, not M saturated by yellow edges. So here again, you have this vertex. Now, if you are able to find out some other matching which saturates every vertices, okay, then we say that M is saturated. The others are, so for example, this is saturated, this is unsaturated. That saturated one. This is unsaturated. What I explained. Let us go to a graph containing all only saturated vertices. These are all unsaturated vertices. Remaining are saturated. A perfect matching is a graph. Graph is a matching that saturates every vertex. If you have any perfect matching, if a matching that saturates every vertex, then that matching is called perfect matching. For example, here we have a vertex which is not saturated by this, so this matching is not perfect. So here, this we have a match vertex which is not saturated by this any vertex, any edge. Therefore, this is not a perfect matching. Similarly, we have a unsaturated vertex. So this is not a perfect matching. Now let us take this example. Here you see in this example, this is a matching. M consists of only yellow edges. This is a saturated perfect matching because every vertex is incident with one of the edges here. Here also, this red edges also perfect matching. This also perfect matching. There is no unsaturated vertex in this. Now it is very important. What I told is very important is a bipartite graph. Okay, we are now going to study matchings in a bipartite graph. This graph is bipartite. Is it bipartite or not? Let us see now. Let us collect some vertices. Okay, you collect vertices in the set consisting of only these vertices. Remaining vertices, you see what are the remaining vertices. So this is the again another set consisting of only this. Now take any edge you take, that edge incident with a vertex of one set to other vertex. That connects one vertex of one set to other vertex. Node edge connects the two vertices of the same set. Okay. Therefore, this graph is bipartite one. Of course, I can write yellow bipartition one V1, another one is V2. You can write this graph, original graph, in this form. One set contains only yellow edges, other one contains only other vertices. Now we take any edge here. Every edge, this edge is nothing but edge between these two. Another edge is a edge between yellow to green. Another edge here, that is green to yellow, this one. In this way, all the edges you can represent here. If it is possible to represent like this, then only we call such a graph is bipartite. No edges incident with two vertices on the same set. Okay. This is nothing but a bipartition version of the same graph originally. Now, in a complete bipartite, matching in a complete bipartite graph. A bipartite graph, bipartite means it can be, a vertexes can be partition two sets. One is V1 and V2. If you find any edge, that is any edge between a vertex of one set to other vertex. There is no edge between two vertices on the same set. Okay, now for this vertex, you see, this is adjacent to every vertex of the other set. There is an edge to from this vertex to every vertex. Okay, that means each vertex of one set adjacent to every vertex of other set. Then we say that such a graph is complete bipartite. Complete means every vertex, all possible edges. I cannot write one more edge here because this is not permitted. So this is complete bipartite graph. Now we are concentrating only complete bipartite graph having same number of vertices in both sets. Okay, number of vertices in the set is n. Number of vertices in the set is n. Second set. So we call this is a complete K bipartite graph. One partition contains n elements, other partition contains n elements. Okay. How many number of matchings in Kn is possible? You can match this vertex. Now you see, consider any vertex here. Okay, this vertex I can match with one vertex. This vertex. Okay, I am getting one pair of this. Later I cannot match this to any other vertex because this edge will take. Then that edge is adjacent to all these edges. Correct? No. Therefore, if you take this vertex, then I can choose any one of the vertex here to match. Therefore, for this, I'm getting n possibilities. N possibilities. If you choose once, twice is over, this edge is over, or any edge is over, then you leave that two vertices which are matched with this. You leave that vertex and this vertex. Then again, still you are getting a complete bipartite graph of dimension n-1, n-1. Correct now? So we have simple calculation. If Fn denotes number of possible bipartite matchings in Knn, Fn is nothing but number of matchings in Knn, then that is equal to n into, because this can be matched into first one or second one or third one. Okay. Once one match for each matching, by deleting that two vertices, I'm getting again kn minus 1, kn minus 1. The remaining matching is equal to fn minus 1. The total matching is how many matchings possible out of the remaining into with this. With this, I can match n into remaining n minus 1. So on recursive, you can write, you'll find out that you can see that this is equal to n factorial because f1 is 1. F1 is nothing but if you have only k11, one vertex here, only one vertex here. I have no choice. I have to match only once. So it finally will get here f1, that becomes 1. So n minus 1, n minus 2. So total becomes n factorial. There are n factorial matchings are possible here. Okay. Now let us see at least one matching. Understand what do you mean by matching? Okay. Let us take one matching in that. I take here three vertices in set. Here three vertices. Okay. What is there? This is adjacent to every vertex. This is also adjacent all. This is also adjacent all. So this is K 3, 3. Now let us find out one matching. I'll match first one with the first one, second with the second one, next one is next. This is one matching. Another matching is first one and first one, these two will change, interchange. This is different matching. The next matching is I can interchange here. This second. This way, so on. Total how many? F3. F3 is nothing but 3 factorial. Because F3 indicates number of matching in K3, 3. That's we already obtained that. Fn is n factorial. So there are total 6 possibilities. I wrote only 3. Remaining 3 can write it. Okay. These matchings are all perfect because this vertex is adjacent to one vertex here, one edge here. So this edge, this vertex is saturated by this edge. So these are saturated. So all the vertices of this are saturated by one of the edges. So this is my matching M1. M1 is nothing but, suppose you take this E1, this is E2, this is E3. M1 is nothing but E1, E2, E3. This is a matching. Matching M contains all independent edges, set of independent edges. Now, how many matchings are possible in a complete graph K to M? Complete graph is a graph such that every vertex is adjacent to each other vertex. Every vertex is adjacent to other vertex. Okay. Every pair of vertices are adjacent. Suppose you take K to N, then that means 2n number of vertices. Number of vertices is E1 here. So this is nothing but an example for K8. N is 4. N is 4. How many matchings are possible in this? How to count? Let Fn be the number of matchings are possible in K2N in this. Then let us see what is Fn. Total how many? How to get total? For each vertex you take here, each vertex. This vertex I can match with any one of the vertex. I can match this vertex with the first one, or I can match this vertex with the second one, I can match this vertex with the third one. Therefore, since there are 2n vertices are there total, except this remaining vertices can match with this. Therefore, there are remaining 2n minus 1 vertices that can be matched with this vertex. Therefore, my Fn is nothing but how much? Fn is nothing but, okay, Fn is nothing but one matching, after one matching, the remaining in, okay, this one matching is possible. Sorry. Network problem. Am I audible? Am I audible?
Only once.
If you have any questions,
Hello?
One.
Hello? Hello? Hello?
Hello.
Am I audible?
Yes, sir, you are audible, sir.
Okay.
I think, but your screen sharing is stopped, sir.
Yeah. Share. Table. Okay. It's okay.
Yes, sir. Visible, sir.
Okay.
uh,
I was explaining complete bipartite graph KNN. There you're getting n factorial ways. Now, how many ways you can find out a perfect matching in complete graph of even order? Here, Fn, suppose Fn is number of matchings possible in Kn to n, to K to n. Then for each vertex, I can match, for each vertex you choose, I can match with remaining 2n minus 1 vertices. For each matching, after losing that vertex and the matched vertex, I'm getting again a complete complete graph on 2 times n minus 2 vertices. For this, I can find out again Fn minus 1 ways matching. For this type of edge, I can find out in 2n minus 1 ways. And for each way, I can find out Fn minus 1 ways matchings. So totally, in simplifying, because these are all odd numbers, inserting some even numbers missing, I can write this as 2n factorial by 2 to the power n by n factorial. It's a very simple counting principle. Now matching, there are different types of matchings. One is maximal matching and minimal matching. So let's see. A maximal matching in a graph is a matching that is not a proper subset of any other matching. For example, let us take this matching. I'll take this edge AF. Next, I'll take the edge BH. I'll take the edge DG. Okay. This contains 3 edges. Okay. 3 edges. Suppose if you insert any other edge here for this set, if you make this a superset, by inserting some other edge which are missing here, for example, if I insert AE, then AE and AF are adjacent. That is not independent. That is not a matching. Matching means no 2 edges in this set have the common vertex. If I insert now AE, AF and AE have the common vertex. AE is not be inserted. B cannot be inserted because BH and BE have the common vertex. Similarly, CF cannot be inserted here because F is common. CH is not possible to insert in this because H is common. DH is not possible to insert for this. Therefore, this cannot be made another matching which is a superset of this. Therefore, this is a maximal matching. This is not a sub matching of any other matching. So this is maximal. Similarly, this is again a maximal one, M2. AE, BH, CF, DG. See, any other matching which are not here, any other edge which is not present here cannot be inserted and made this bigger matching. Therefore, this is again a matching, maximal. So these are 2 examples for maximal matchings. So both are maximal, but M1 contains less number of edges than M2. Okay. The one which contains maximum number of edges is called maximum matching. So a maximal is different, maximum is different. So if you take M1 and M2 only, there is no other matching is possible in this, then we can declare M2 is the maximum. Else we may have. Now a maximum matching is always a maximal matching. This is a maximum matching, which is a maximum, always maximal. And converse is not true. Okay. Now, why I'm declaring this is a maximum matching because it saturates every vertex here. A matching which saturates every vertex is actually a maximum. Maximal matching because this is maximal matching, which is not saturated. That will not saturate E. So that this saturates that vertex also. Therefore, this is maximum. Now let us take an example, the real situation where matching is essential. In usual sense, we have a marriage problems, okay, between a vertex of set M and W. M is the set of all men who wanted to marry. The W is the set of all women they're ready to marry. Now a marriage is nothing but a matching. One vertex of this set matches exactly one of the vertex of this, not two. Okay. Therefore, there are 4 vertices in M. There are 5 vertices in W. If you find a matching, that cannot be perfect because I can match maximum 4 men here with 4 here women. Cannot possible to match more than 4 here. Okay. Therefore, at least one of the vertex is not saturated by any matching. Therefore, that is not perfect matching is not possible here. But can we find a matching which saturates only all the men? That is possible because there are more than maybe possible. I don't know. Maybe possible. There are 4 men here. More than 4 women here. Bridegrooms are there. Therefore, it is possible. But here, can you saturate all the women here? No, not possible because to saturate each one, I require at least 5 here. It is not there. Therefore, you can think about saturation by a matching which saturates either M or W only, not both. Okay, both saturates both means that's a perfect match. Now, this is not a complete bipartite graph of order same KNN. This cardinality of M and W are different. Okay. Now, is it possible in this case? Can I arrange a marriage for these men such that so that everybody get married? Possible or not? If possible, then that matching is called a matching which saturates M. For example, okay, now by trial and error method, I can match something. A match here. If not possible, then trial and error method. Very difficult because this is very simple one. Real situation, there are not only 4 men in India. There are several. Here also there are several. No, so there are some likes, unlikes, both are there. So it is impossible to find out by trial and methods. For that we have Hall's theorem. Hall's theorem tells that some certain conditions satisfy, then it is possible to find out. What the condition is? It tested that you take any subset of this, any subset. This M contains total 4 elements. Therefore, 2 to the power 4, 16 possibly, 16 subsets contains null set also. You leave that null set. Other than null set, there are 15 possible sets you take. I take one subset here, one subset of M containing A and B. Okay, you see what are those vertices which are adjacent to that. That means what are those pairs here liked by these two. Okay, let us see now. Okay, this is A likes E, F, and B likes F and G and I. Okay, so there are how many people, how many vertices are there in this total union here? There are 4 total. Here there are 2. So 2 subset containing 2 elements here match to more than 2 here. You check for this. Therefore, mod S is nothing but here. This is S. The neighbors of S is more than S, cardinality of S. This is not only for this. There are total figure 4 vertices 2 to the power 4 minus 1. That is 15 possibilities are there. For every possibility, this condition should hold. Okay. Let us check for other possibility. I will take the subset containing A and D. Let us see the cardinality of S is now 2 because this contains 2 elements. Let us see the neighbors of this. Neighbors of this contains 2, here also 2. So right hand side contains 4 vertices. Okay. Left hand side is 2. So this condition holds. Let us again verify for some other set. This also subset, no? B, C, D. So left hand side is 3 now. Left hand side is 3. right hand side is neighbors. Okay, so there are 5 here. So 3 less than or equal to 5. The condition holds. Now you can take all vertices also. There are 4 here. So matching here, the 5, this condition still holds. You can check the remaining. So the condition holds. If this condition holds, Hall's theorem tells that there is a perfect match here. Also, if there is a perfect matching, definitely that condition holds. If and only if. Okay. Now that is given by Hall's. If an MW by graph G has a matching that saturates M, if and only if this condition n of S, neighbors of S greater than equal to number of elements in S for every subset S in M. Converse is not, reverse is not possible. We cannot find out any matching which saturates W, because if you take some vertex here, if you take these 3, there are 3 vertices, neighbor contain only 2 vertices. This condition fails. Therefore, definitely you can say there is no matching which saturates W. Now let us try to find out matching. Okay, I'll try it by trial and method. First I came to know that there is a possibility. The graph theory, the beauty of the graph theory is that it says if there is no, then don't do it. So it minimizes our work. Now instead of go on searching, finally you conclude after 10 days, not possible. So that type of problems started. Graph theory started with such a problem. No, conical bridge problem. Okay, infinite possibilities. Finally, somebody should say within a fraction of a second that it is not possible. Don't do that work. Now Hall's theorem tells that you can go for finding a matching exists. Now let us start find out. I now I will take this word H. Okay, H has no other possibility. H should be matched only with the D. Okay, that's the only possibility. Maximum I want to take maximum matching. Okay, maximum coverage of M. H M. Once D is over, then I cannot think about I. D I is not possible. Then I should be matched one of this. Okay. Okay, now there is other girl here, G. G can be married only B. Therefore, we'll make that matching first. Okay, that option is now go on. B and D has gone now. So C have the possibility either F or I. F or I. That's all possible. And A have a possibility E and F. Okay, which one is now your take? Which one? Anyone? Okay. CI will take. Let us take CI. Then CF is ruled out. F is ruled out. Then A have the option. Either can marry F or can marry E. Okay, it chooses E. So this is the maximum matching. This is the maximum matching, maximum matching, which saturates all the vertices of M. So here F is left. If you're matching Hall's theorem, proof of the Hall's theorem is very beautiful. If you matching M saturates, then certainly this condition holds. If this condition not holds, then there are number of elements in W is less than number of elements in there, because this condition holds for every S. Then certainly this condition should hold, and Connor's part is important. Suppose this condition holds. Suppose there is no matching. If possible, there is no matching M, which saturates at least one man here. That is not possible. At least one M is possible to saturate. Then what happens? This M is not married with any other. So from this M is connected, because this graph is connected. This M should be connected. From M I have to go somewhere. I cannot go to here. I have to go to somewhere only, because the graph is connected. I have to go somewhere. So there is a girl here. It's not married. This M, definitely. Now what to do now? From this girl, you see all possible matched men here. Okay, for this girl, then the only matching is here. Okay, that means from this vertex, all those vertices which are reachable from this vertex, you travel first. Okay, or because taking alternate paths. Okay, alternate paths. From this, I have to go. I have to go only unmatched edge. From this, I can go for matched edge or unmatched edge. I don't know. If it is not matched edge, don't go. Matched edge, go. If it is not matched, leave that. Okay, don't go anywhere. This one. Finally, you collect all those which are reachable from this here. and all those which are reachable from this M. Now, this path, if you take any alternative path of unmatched matched, definitely that should end here. That cannot end here. So any path start from M should end here, because I'm assuming that this M is a maximal matching. I cannot make a superset for this. This is the maximum matching. The cardinality of the set is maximum, I assume. Suppose what happens? Suppose if the vertex starting from this vertex, if the path ends here, that means this edge is a white edge, unmatched edge, correct? No? So what you can do now, you see this unmatched, one matching, unmatched, one matching, unmatched. So in this, there are two matchings, three unmatchings. What you can do now, you can match this. You make this is red, this is blue, this is red, this is blue, sorry, this is red, this is white, this is red, this is white, this is red. You can make that. So I can take that M, I can remove these two edges from M, and I can include these three edges to M to make them bigger matching. Okay, that is the contradiction of my assumption. M is maximum. Therefore, every matching from here should, every edge from here or path from here, alternative path should ends at the set W only. Okay. Now, afterwards, let T be a subset of this. Let us take this is subset. Set of all nodes reachable from M by an M1 alternative path. Okay. Each edge, I already explained this. Not possible here to end. Now what to let yes, you take this is yes. Yes is subset of W, which are reachable from H is subset of M, which is reachable from M. This vertex M, unmatched vertex M. Then what you can observe, there is no outside this, there is no vertex outside this T, such that that vertex is adjacent to this M. Adjacent to this M. Okay. What happens if not? Suppose if you have M here, then if that is adjacent to this, because if there is some S here, which is adjacent to this, okay, then what happens now? This is white edge, this is red edge, this is white edge. So what you do now, we make this is red edge, this is white edge, this is red edge. I'm getting a new inclusion of these two edges. By deleting this, I'm getting a new matching, which is maximal than this, maximum than that. That will get a contraction. Okay. Therefore, it's not possible. There is no vertex W which is outside this. Now, by this, we can conclude that how many number of elements in S, how many number of elements in T. Number of elements in T exactly one less than number of elements in S. Okay. Now, hence, what is neighbors of S? Neighbors of S are only the vertices in T. The number of vertices in T is exactly equal to one less than the number of vertices in S. By assumption, this mod S is less than equal to N of S. You replace this N S by N of S. I'm getting equal to N of S minus 1 is strictly less than N of S. I'm getting a contradiction. N of S strictly less than N of S. So I'm getting a bottom a contradiction. So this is the converse part of this. Now, if G is a bipartite graph, then the maximum size of a matching in G is equal to minimum size of vertex cover. So we can, how many what is the maximum matchings are possible from here? Previous theorem test, there is a possibility of getting a matching. What the maximum possibility? For that, we have definition of vertex cover. What is mean by vertex cover? Vertex cover is the set of vertices. Out of these vertices, I choose some vertices which cover all the edges. That means every edge is incident with one of the vertices there. Suppose if I take now this vertex covers these three edges. Okay, this edge is not incident with that. Okay, now I choose one more vertex here. This vertex. If I choose this vertex, that will cover these three. Okay, not all the edges are covered now. I want now new vertices somewhere. Okay, I choose now this one vertex now. Okay, this vertex, if I choose these two vertices are covered, still I have one more uncovered vertex, edge. For that edge, I have to choose one more vertex. Okay. Okay, I have chosen now 4 vertices to cover all the edges. Okay, now my vertex cover is contains these 4 vertices. Okay. You can think now, can you find this, can be another covering, vertex covering containing less than 4 vertices? What we are interested is, what is the minimum number of edges, number of vertices which covers all the edges is nothing but vertex cover number of. That is exactly equal to maximum size of a matching. This theorem tells, Koni's theorem tells that if G is a bipartite graph, then maximum size of a matching in G is equal to minimum size of a vertex cover. Proof is very simple. If you choose a matching now, if you choose a matching, let us now take the matching. If it is maximum, what else? If you choose a matching, a maximum, this is maximal matching, not a maximum. I choose just one maximal because not any other vertex, any other edge is incident to one of the edge here. Okay, a matching is maximal. Then we have every edge which is not selected is incident with one of the selected edge, one of the edges in the matching. Then only that matching is maximal. This is maximal matching. See, any other vertex, red, white vertex, incident to one of the red edges. Now, for each for this edge, you choose one of its end vertex. Okay. For this, choose one of the end vertex. For this, choose one of the end vertex. For this, choose one of the end vertex. Okay. This, by this way, this already covered this one. Correct one. Cover the edges of the covered the edges in the matching. This see, these vertices covers all the edges which are in the matching. So red edges, this covers red edges. Correct one. Therefore, matching how many edges are there here. Okay, that much you choose that covers the edges in the matching. So for cover all the vertices, we want more than that. Okay, vertex cover is more than equal to maximum number of edges in the matching. On the this is the one way. Other way equality to prove. So number of what in the matching should be greater than equal to number of elements in the match. Vertex cover is C. Number of vertices required to cover all the edges always greater than equal to number of edges in the matching. So, okay. In the reverse way, to find the reverse way, you choose any matching, like a vertex cover. This is the vertex cover, you know that. This is vertex cover. Vertex cover covers all the edges. Cover all the edges, okay? Vertex cover covers all the edges. For each vertex, you choose one of the edge, exactly one of the edge. So for the number of edges in a matching, exactly more than equal to vertex cover. For each vertex cover, I can choose one of the vertex, one of the edge incident from that. Here is one of that. This may cover, saturates all the vertices in one set. That means this may be maximum or may not be. But if it is not maximum, I require more than that. Therefore, what we have is these edges to cover all these edges. What you want is smart C less than or equal to mod M matching the come. Therefore, on both way we proved. Therefore, we conclude that mod C less than or equal to M, M greater than or equal to less than or equal to mod C. Therefore, equality holds. Now, if you take a matching now, conversely, if you take a matching now, you take the vertices which are in the vertex cover in set X, that is R, which are in Y, call that is S. S is nothing but cover, vertices cover in the cover in X. S is nothing but vertex in cover in Y. Now, remaining which are not there, S bar, this is nothing but R bar or X minus R. Let us now take a graph G1 which is induced by R union Y minus S. This is Y minus S. Let us take this graph induced by this. Okay, that means graph induced by that, all these vertices. Let us take now another graph G2 induced by these two. Okay, these two. There may be some other vertex left. Okay. Okay. Then, how many edges are there required to cover this? Hall's theorem, there is a matching M1, there is a matching M1 which saturates, because number of Hall's theorem holds for this, because this two elements you take, here you are getting more elements. If you take one element, definitely you are getting more than one element here. Here also there is a matching which saturates R. Again, there is a matching which saturates S. Okay, so I am getting a matching here which saturates all the elements of R as well as all the elements of S. That means it saturates all the elements in my C. Therefore, my matching is M1 plus M2 is nothing but the purpose. This is a very simple idea behind the proof. Now let us go to, not going to any proof in further, going to now some problems on in real life problem, assignment problem, the marriage problems. Assignment problem is a problem to find maximum cost, okay, for n assigning n jobs to n persons, traversal with maximum cost or maximum cost path, or it is a traversal with maximum cost. The underlying model of the graph is a weighted complete bipartite graph. Assignment problem is not job assignment problem. There we are looking at minimum cost. Okay, this is the dual of that. Underlying model of the graph is a weighted complete bipartite graph KNN. The weights Wij to each wedge. For example, let us take this one. So this is the A, B, C, D, maybe the persons. Capital A, B, C, D, E are the jobs. Okay. If you give A to capital A job to A, okay, then we're writing H weight here, Wij. This is one, this W11 I'm getting. The weight of this H gives the profit I'm earning. See, this is not a job schedule problem, don't confuse. So I am a broker. If I assign this person A to this job, I'm getting commission. My aim is to get maximum commission by assigning the persons to the jobs. Okay, who gives the maximum commission? I'm assigning for that. So A to A, suppose here A, if I assign to A, I'm getting a profit of 4 rupees. If I assign the person A, the job capital B, I'm getting a profit of 1 rupees. Okay, so this is the way, this is the metric representation of my commissions. Okay, my intention is to get the maximum profit. Okay, for that Hungarian method we are going to apply. The solution of the problem is maximum weighted matching. Okay, the matching is A which adjacent to one of the vertices, one matching. The number that commission I'm getting, that Wij, that we are writing as the weight of the H. Okay, sum of all the weights of the matching is nothing but sum of all the weights in the edges in the matching is called weight of the matching. For example, now I am going to solve this problem. This problem assignment is given here in the table. Commission is indicated in the form of a matrix. I'm going to apply Hungarian method to find a minimum cover, so as to get a maximum profit. Okay, maximum matching is equal to minimum cover. So that theorem I'm applying using Hungarian method. For that, what to do is, so here the matrix you represent is the matrix, the worst person A, if I assign the job capital B, I'm getting 1 rupees profit. This is matrix. What happened? Mute. Now, if you see the matrix you read now, if I assign a job capital C to a job to a person small a, I'm getting a profit of 6. That's the maximum profit I can earn from A. Okay. Similarly, the maximum profit I can earn from B is 7. Maximum profit I can earn from C is 8. Okay. These are the possibilities. Now I am going to think practically what is possible to happen. Okay, now what to do is you choose the maximum here, take the maximum out. That means you remove maximum from each row. 6, 6 minus 4, 2, 6 minus 1, 5, 6 minus 6, 0. Okay. This maximum, you subtract each one from this maximum. Okay, that is the losses I'm getting. If I assign this, I'm getting a loss matrix. If I assign this person instead of 7, I'm losing 2 rupees. This is the loss matrix I'm getting. Similarly, so 8 I took an outside. So subtract each one by 8. I'm getting this. Then you see the zeros. The first one, first row, first third column contains 0. First row corresponds to A, third column for C. So you write an H from A to C. A to C. Okay. I want to lose the minimum profit. This is the loss matrix. Okay. I'm thinking to get minimum loss. Now the second one, second row in fourth column, second row B, this is capital D. So B and D, you write an H. Okay. Now this is C and E, write an H. Similarly, last one D and C, write an H. Okay, this is an H. Okay, this is the representation for this matrix. Okay, bipart representation. Then what to do here is now then you choose a minimum vertex cover here. Okay, choose the vertex cover here. So that means I'm choosing now C. If I choose C, that will cover these 2 edges. What are the edges? CA and CD. Next, if I choose D, it will cover the edge BD and D. Correct now? Still one more edge left. To cover that, I can choose E or C. I choose now C. Okay. You can choose C also, no problem. Okay. Okay. Now this is a vertex cover. Once you get a vertex cover, then see the vertex capital C, capital D. These are the columns. This small c, small a, b, c are rows. Okay. Row C, small c, row, capital C, capital D column. Okay. You block that. This is capital C. Next one is capital D. Next small row. Block it. You see the remaining elements in the matrix. Okay. Then minimum loss is 1. Correct? No? Out of this, minimum loss is 1. You subtract 1 from each of the entries in the red box and add that 1 to the elements in the intersection of rows and columns, selected rows and columns. So this 3 is there here. This is the intersection. This is intersection 4. 4 should become 5. 3 becomes 4 because they have to add this. Remaining all just subtract. This is 1, 4, 2, 7. 6 and 5 is unaltered. This don't disturb it. Only all those numbers inside red should be reduced by 1. All those numbers in the intersection should be increased by 1. The rest should be kept as it is. Now, in that way, I'm getting a new matrix. This matrix. Okay. For this matrix, now start the process. Same thing. Go to step. Starting one. Here you now write the matrix for this. You write a graph for this. A to C. B to D, B to D, second one, B to E also there. Next C to E is there. Then this is D, D to capital C. The last one is E to capital D. Write it. So now again find out a vertex cover. C is the one covers 2 edges, and D covers 2 edges, and one more. I'm choosing E now, covers 2 more edges. Okay. This is the vertex cover. Again, choose the columns C, D, and E. No rows. You choose the column this 3. Again, you find a minimum. Okay, non-chosen columns or rows. Then subtract 1 from each. Add. There is an intersection. There is no intersection here. There is no necessary to add. And remaining unaltered. These are only decreased by 1. There is no intersection here. So again write a graph for this. Okay, go on, repeat the process. Again, write a graph for this. Wherever 0 is there, you write an H on that. Okay. Okay. Now let's see. It's completed. Now find a vertex cover here. Again, find a vertex. Okay. Okay. Now this process ends because Each row contains 1 0. Each column contains 1 0. Previously, it was not there. Okay. Whenever there is a 0 in every column, when there is a 0 in every row, stop. Every row and every column, stop. Now we find a matching in this. Perfect matching. Find any perfect matching in this. So what to find perfect matching? C cannot be matched anywhere other than E. Once E is matched, we cannot be matched with B. Okay, there is no option for B. B I have option now either D or A. Okay, I'll choose now D. Once I choose D, I have no option for E. E should be matched to B only. Perfect matching I want to find out now. E should match it on B only. Once B is over, D cannot be, then D should be C only. These are the only possibility. Okay, D should be C only, A should be B. These are the only possibilities. D should be there. D is matched to C. After the matching C, A cannot be matched anywhere other than A. That is the final one. So you're getting this is the perfect match. Then you go to the starting table, starting matrix. A to capital, small a to capital A. If I assign capital A, small a to capital A, I'm getting 4 rupees. B to D, I'm getting a profit of 7 rupees. All that profit you add right on the edge. Then add all this. 4 plus 7 plus 6 plus 6 plus 8. That was the profit, maximum profit what we are getting. Okay. That is nothing but 10 plus 24, 20, 31. Okay. If you choose any randomly, any other matching, definitely you won't get more than that. So this is method. Another one is matching and Hamiltonian circuits that are all one and the same. See, different concepts in graph theory can be utilized nicely. Matching and Hamiltonian circuits. Okay. Traveling salesman problem, TSP, Hamilton is nothing but a finding Hamiltonian cycle of minimum weight. Okay. For example, Hamiltonian cycle is a cycle containing all the vertices exactly once, correct? Now I'll start from A. I'll go to B. Okay, there is some algorithm available to find out the minimum weighted Hamiltonian cycle. That is nearest neighborhood method. For starting from A, from standing at A in the junction, I'm thinking to go somewhere with minimum cost. Okay. From A, if I go here one, I'm getting, I have to spend 2 rupees, I have to spend 4 rupees or 5 rupees or 4 hours then maybe. So I'm thinking to go nearer one, nearest neighborhood, that will be. After setting in B, I am thinking now, can I go to 2 or 3 or 4? So I think now 2 is better, because this is the nearest one. By visiting after visiting C, from to go out of the C for the non-visited vertices, not for this. Okay, non-visited vertices. I'm thinking now 5 or 6, which is better? 5 is better because minimum. From D, I have no option because already all the other vertices that this is the only option. I have to go to C. Afterwards, I have returned back that 5. So my total cost of travel. Cost of travel you count now. These are the cost now. 1 plus 2, 8, 10, 15. Okay. I got a travel too by covering all. I'm spending by 15 rupees or 15 hours or $15, whatever. So 8, 10, 15. Okay. Okay. This is the cost of the car. The total cost of the travel is 15 units. Okay. That is the minimum. This is the method of finding the Hamiltonian cycle with the nearest neighbor method. But can you find another cycle which is cost is lesser than this? Some other way, not by any methods, some other calendar method. Okay, now let us see from A to B. I'll go like this. I will not choose the nearest neighbor. I'll go some other way here to E. Afterwards, E to here. Then I'll go here. Then I'll go here. Then I'll see what is the total cost. It is nothing but 1 plus 4 plus 2 plus 5 plus 2 is 14, less than that. So, okay, nearest neighborhood method gives Hamiltonian one solution, but that is not optimal. Sometimes maybe. Okay, so there is no better algorithms available till today to solve any traveling salesman problem. So some other approach will go now to make this attempt. I will write now that complete graph as a bipartite graph representation. I told in the beginning, I started with this, every complete graph. Every graph can be represented as a bipartite graph by replicating the vertices and writing the corresponding edges. This is the bipartite representation of this graph.
Hello. Hello.
Screen sharing option. Hello? Hello? Hello?
Yes, sir.
Screen sharing option.
We have given, sir, co-host. You are the co-host. You can share, sir.
Available?
Yes, sir. Visible,
Okay.
sir.
Okay. What I'm trying to tell is now, traveling salesman problem is nothing but finding a Hamiltonian circuit in a graph that is equivalent to finding a matching here, okay, of maximum weight, minimum weight. For example, let us now find a Hamiltonian cycle here from A to B, that's nothing but A to B here, then B to C, find out the edges here. So C to D, write on the edge here. That is identify such that. Okay. Once you find complete Hamiltonian cycle here, I'm getting a resultant graph. Here is the matching in the replica bipartite graph. I'm getting matching here. Okay. Again, this is one factor. Hamiltonian cycle is nothing but two factors. So two factor is a subgraph of G. Every vertex of degree 2. Need not spanning. Okay. What the remaining cycle I'm getting again is one more two factor I'm getting. For every 2 factor, I'm getting here a 1 factor. So 1 factor is nothing but here, and then the replica bipartite graph is exactly equal to the Hamiltonian cycle. And the conversely, another one, this Hamiltonian cycle, another one by using the Euler circuit. You take Euler circuit now A to B, write the edge here, correspond Euler circuit trace in the replicated vertices. See now B to E, right? B to E again. I'm trying to write a Euler circuit as well as a bipartite graph for each Euler circuit. For each Euler circuit, you can write a bipartite graph. For each Hamiltonian circuit, also you can write a bipartite graph. You can find a matching. Okay. Now, after completing this Euler circuit, now let us find out a matching in this. There are 2 matchings. Each matching I can find out now corresponding to each matching, identify the corresponding edges that becomes Hamiltonian circuit in that. Hamiltonian circuit in that. The problem, traveling salesman problem can be converted into maximal matching problem or minimum matching, both. Okay, instead of that, so we have another type of minimum cost cover. So traveling salesman problem, we are having only one salesman. We are thinking to send that salesman to cover all the vertices and return back to the office by traveling at the minimum cost. Instead of that, we can distribute parallel processing, that we can take 2 persons instead of choosing one person required one full day, suppose, to cover all the places and return back with some cost. Instead of that, if you choose 2 persons with half of the salary, because they will, both of them will return back within half a day by covering 50% of the work with the less cost. That's possible. See, for example, in this graph, see, I've taken the replica of this graph and this is the corresponding edges are written here. What is the Hamilton? If I assign a job to single person, you see to cover all the vertices, I require now 2 plus 4 plus 2 plus 3 plus 1 plus 3. Okay, this may be the minimum cost. You don't have any other alternate path. So I have to spend 6 plus, this is 8, 6, 8, 11, 12, 15. So 15 rupees I have to spend, 15 units of amount I have to spend for a single person. Instead of that, if we choose 2 persons, okay, to cover first 3 vertices was first one, second 3 vertices, remaining 3 vertices by second person. First person will require 7. The second person required only 6, correct? No, 6 plus 7 is 13. I'm getting less than that. So job also finished within 50% early, and cost also reduced. So this is nothing but a minimum cycle cover. Okay, that's nothing but I'm going to find out Hamiltonian circuit. Instead of Hamiltonian circuit, we are going to find out 2 factors. 2 factors are the subgraphs. They need not be connected of degree, all regular graph of regularity 2. Okay, and another problem. This is another, that means another way of looking the same problem in matching, as if you find a matching here, finding a matching here, that 1 factor is exactly equivalent to finding a 2 factor there. 2 factor. That means this red colors are nothing but a spanning subgraph. This is of degree, regular of degree 2. Again, one more matching, I'm getting 2 factor. Again, one more matching, I'm getting there, one more 2 factors, or one more 2 factors. And finally, we'll go for the marriage problem again, the stable marriage. When you say marriage is stable, so this is the first, here there is a preference list is given. So instead of A, B, C, D, E are men. These are women. So we take F, G, H, I, K. These are the women here. There's the men. They want to marry. You will take this now. Preference is there. A preference list is given here. A will prefer F more than G, more than I, more than H. The preference list. K is the least preference for A. F is the most preference for A. Okay. So you have to satisfy their preferences at least. Then you have to make a matching between them. For example, suppose somebody matched this way. This happens. A married H. A married H. Then what happens now? F married C. This what happens in this matching. B is matched with some other. Okay. For example, I'm taking note. Now let us look into the married couple A and H. Married couple A and H. Okay. A prepares A married H, but H is the least preference. A prefers F. A prefers F. That means A prefer F more than H. A likes F more than H. The same time, let us see what happens for F. What happens for FC? F in the preference list of F already married C, but in the preference list, A is more preference than C. See, so F is preferring more than A, more than the C. Then what happens? This marriage breaks up. So there's marriage takes place here. So the previous marriage is unstable. So any matching, you should not get any such type of edges. Then that matching is called stable marriage. Stable matching. For example, how to find a stable matching? Okay, there are so many algorithms available. So this is one of the example for a stable matching. Okay. So now I told how to check this. Okay. Any matching take A preference list you check. Any other vertex is not adjacent to A is more prepared than F, and also that is not F is also not prepared. Then there is the breakage definitely. Now there are so many algorithms to find a matching or to make a marriage between them by satisfying all their conditions. Okay. So one example I'll take now and stop. So now this is the boy's preference. Will give the preference to Y first. Okay. So what happens now? I'll ask A one by one. I'll ask A to want to marry. Now A's first preference is F. Okay, he wanted F. Then I'll ask B. Second boy, in his list G, H, I, K, F. G is the first preference. Okay, that is available. Girls are available. He proposed the C. In C's list, F is the most. So C will also propose F only. Okay, marriage will not taken place now, just a proposal only. D in D, H is the most preferred one. Okay, you will prefer H. Next E will prepare K. Okay, this is the preference. Then I will ask F. There are two persons preferred, F, A and C. Then among that two, F should choose. Okay, F will choose A or C in his list. In her preference list, A is more preferred than C, so F will prepare A. Okay, F will prepare A. This marriage will take place. Okay, ultimately, and here also G will prepare B. H has no option, only one proposal. She has to. There is no other choice. Okay, now this marriage will take place. Okay. Once marriage takes place, no other should propose them. Okay. Now A and F are matched, B and G are matched. Only C is unmatched now. Now again the algorithm starts with the step 1. C start to propose. She has no choice. She has no choice. Only in this reference F, G, I is the only F are already over. Okay, then this C should marry I only. I has no choice. I should marry. This is the one marriage takes place. This is the algorithm, which is first boy proposes, girl selects. Okay, another way, girl proposes, boy selects. Both use the same stable marriage. This is the second one that I skip now. Okay. Any questions? Can I stop now, madam? We have time? We have time now?
Yes, sir. You have 15 minutes, sir.
Oh, okay. Then I'll continue. Now, the algorithm, same algorithm, will start with from girls from side. Okay. Now, the algorithm, which runs with the girls will propose first. The F will propose to whom? To B first, okay? Because preference is B. Then I'll ask girl G. G will prefer B, okay? Next I'll ask H. H will prefer C, okay? I will prefer E, okay? K will prefer E, okay? Now you have to choose, wise to choose out of these proposals. B likes out of F and G in this list. F and G. G is more preferred than F. Therefore, B will select F. Okay. Sorry, G is more. B will select G. G is more preferred than F. Next to the C. C will, there is no choice. C should select here. And E has the choice now. In this list, I and K, out of I and K is most preferred. E will select K. Okay. This marriage will happen. Next unmarried girl. Again start to propose. F will propose only unmarried, either A or D. In A or D, A is most preferred. So F will prefer now A. Next I will prefer out of A and D. A is most preferred, so I will prefer A. Then selections to A. Choice is left to A. A will choose now most out of F and I. You choose F. Okay. This will reject. So then this marriage will take place. After that, there is no choice. I should propose D. D should accept I. That's all. This is the another marriage. This is the stable marriage. These are all the algorithms in runs in the bipartite graph. And another Hamiltonian path property is to find a shortest strings. Okay. This is a hypergraph structure. Okay. Each vertex represented by a binary bit of length 3. That means each place bit is either 0 or 1. There are 3 bits, sorry, length is 3. Therefore, there are 8 possibilities out of a binary bit of 0 and binary bit of length 3. 0, 0, 0, one place 0, 1, 0, other place. Okay. Now, 2 vertices labeled with that binary bits of length 3 are adjacent whenever they differ by exactly one place. For example, 0, 0, 0, and here 1, 0, 1, 0. The second place will differ, therefore there is an agent. And 0, 0, 0 and this 0, 0, 1 differ in the third place, therefore exactly one place in the third place, therefore they are adjacent. And 0, 0, 0, 1, 0, 0 differ in exact one place, they are adjacent. Okay, this type of structure they're constructing. They're also a part of Kelly graph and hyper cubes. So that are used in architecting processors in the computer. Okay, so for computer architecture, and it can embed any algorithm find the biggest numbers and all in this structure. There are so many other possibilities. Now my interest is not that one. For such human DNAs, I want to convert this. The same graph, I will not write the edges which are differ by them. What type of edges are right now? You see here 0, 0, 0, 0, 0, 0. The last 2 is 0, 0 here. That should be the first 2 in other one. That means this here 0, 0, 1 is there. This one 0, 0, 1. The last 2 is exactly equal to the first 2. Therefore, I am writing an edge from here to here. Again 0, 0, 1. The last 2 is 0, 1. 0, 1 is the first two bits in 0, 1, 0. Also 0, 1, 1. So I'm writing a directed edge from that vertex there. So this way I would represent the last 2 bits is exactly equal to the first 2 bits. Then there is an edge from that vertex to the other vertex. In this, now I want to find out a Eulerian circuit in this. Okay, no, sorry, Hamiltonian circuit in this. So what Hamiltonian circuit? Then what type of why I want Hamiltonian circuit here is start from 0, 0, 0. This color coincides to 0, 0, 0. Okay, 0, 0, 0 to go to C, getting this. See exactly. See exactly it coincides. finding Hamiltonian circuit. After finding Hamiltonian circuit, Hamiltonian path. After finding Hamiltonian path, covering all the vertices, I will get back. I will get this string. So each 0, 0, 0, 1, 0, 0. This represent, each vertex represents one character, human character. Okay. If your DNA contains this, this is the shortest string. Okay. What the length of this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10. Shortest string containing all the characters. See, you break up any 3, that becomes one of the character. Okay. So this is this type of just finding Hamiltonian path in this such a graph. To find a shortest, the structure of shortest length is very essential in bioinformatics. Another type of structures are nothing but our Kelly graphs. This hypercube. In this routing, to route, you have to give the instruction ABC. If you give the instruction ABC, starting from any vertex, for example, start from here, it will read ABC. It will read A. Here, see, identity element E. E to A is red color is A, green color is B, white color is C. Okay, this is the A edge. If you write A, immediately will go to red edge. Okay, then B, then C, then B, then C. It will reach AC. If you give the instruction ABC, immediately it will start from wherever the pointer is there. It will reach. It will travel that way. Suppose the pointer is here, it will follow that ABC instruction ABC. So A, and then green, then red, white. It will reach this point. This is the way you can do. This is the way you have to give the algorithm for routing. For example, if you write ABC, CAB, ACB, if you give this instruction starting from this vertex, you give ABC, it will travel like this. Correct? No? A, B is green, A is red, C is white. Okay, next. CAB, you start from same one, CAB. It will start from CA, A, B. You reach the same point, ACB. From same one, ACB. It will reach the same point. Okay. So these are not different. This is nothing but a method of routing. In this structure we are constructing using the groups and graphs. Okay. This is called hypergraphs, hypercubes. In that, later algorithms are very easy. This type of algorithm is very easy to find out. And if you say how to find the biggest of 2 numbers, these are all ABs. These are all vertices are nothing but memories. It will locate. It will travel. It will. There are some other algorithms will identify some other paths to travel and get the results. Some other applications are a crossbar applications. Okay, in scheduler, corresponding scheduler graphs are there. I think it's very much more now. Thank you. I thank the organizer for giving me the opportunity. Sorry, in between there are so many network issues. In spite of that, your patience, I thank for your patience. In spite of that, all these circumstances. Thank you, madam. I finally, once again, thank the Radha Gupta madam and all the faculty members of mathematics faculty members of Dayana College and principal and all the management for giving me the opportunity.
No problem, sir.
Thank
But you gave an excellent presentation and wonderful applications. Really, we were not knowing such good applications are there of graph theory. And presentation was also very unique and very nice, sir. Thank you so much. So all those hindrances which came and which are not in our hands, it is all network issues. None of us can help it. But all that is nothing in front of your presentation. Thank you so much, sir, for your wonderful presentation.
Thank you.
Let us ask the participants if they have any questions for sir. Are there any questions from the participants? Let's see the chat box. No. I don't see any questions there in the chat box also. But I'm sure many would have got some new ideas.